Our next session will be led by Guan. He is a principal data scientist at Raymond James. Che's experience has been in solving financial industry problems using quantitative research and data science. Until recently, Che has been working in developing quantitative strategies for FX and digital assets at Noble Capital International. Prior to that, he was developing data science solutions across retail and wholesale businesses at JP Morgan Chase and credit rating R&D at Dun Bradstreet. Che received an MS in Statistics and PH.D. in Electrical Engineering from University of Connecticut. His interests include artificial intelligence and quantitative research with applications to the financial industry. Please join me in welcoming Che Guan to the stage.
Got it. Well, thank you very much for having me here, and thanks for the introduction. Today I'm going to talk about my recent previous research, a side project on using machine learning for asset allocation. The key idea is to use. It's pretty simple. We use ML method to forecast individual asset returns with prediction interval constructed at the horizon. And then at the horizon, we have the ex-ante portfolio. We further optimize it, and then we further construct two portfolios. One is minimum Sharpe ratio. The other one is maximum Sharpe ratio. The other one is minimum variance portfolio at the horizon. We repeat this process in a moving window miner so that we have the dynamic allocation. With a proper trade-off rebalancing frequency and transaction cost determined by turnover rate, as well as a constraint for forecasting return fed to the optimizer, the approach shows some promising results from backtest. So before I show the numbers, the next few slides, so first I would say please don't make any decision or investment on the numbers here. This is just a toy example. This it's not a real one. There are many things we haven't considered, so please be cautious. This is I read a paper last year, so this is a very interesting method. It uses deep learning method to forecast the return and then construct portfolio. So for simplicity, I just use the assets from the paper. So there are 11 assets selected from this paper. They have 4 stock ETF. They have 5 bond ETFs. They have rates, and they have energy fund. I think, well, it's pretty representative. Also, it's kind of liquid, so we don't have to consider the liquid cost. Now, with the assets selected here, so we're going to first conduct the data analysis and feature engineering in the first step. There are a few, so later on, you're going to see there are some hidden information which may not be captured by the linear regression model, but I think machine learning model can capture some of the hidden features within the data. Now, with the data, but there are many machine learning models in the zoo. Yesterday, you may heard different talks. Several speakers, they mentioned several machine learning models for for prediction. So here, I screened 10 popular machine learning models, and then choose a candidate for prediction. To further quantify the forecasting accuracy, I have the prediction interval constructed at the horizon. So the idea is, suppose I have a time t, so I make the prediction, I have my prediction, I have confidence interval that's lower boundary and upper boundary. So I'm here. The idea is if my prediction is far away from actual at time t, and then I'm not confident to use the prediction at t+1. So the idea is if my actual is here, I just replace my prediction with the lower boundary. If my actual point is here, I just replace my prediction with the upper boundary. In another word, I use prediction interval to rule out some extreme values in the prediction. This is a similar idea, well, not similar idea, but if you look at the robust optimization, so whenever there's a big change in the return or correlation matrix, your allocation would be very different. So here, here we just rule out some extreme values in prediction so that we can have a proper mean fitted to the optimizer. This is all right. So and then so with the help of prediction interval, we can reduce a little bit uncertainty, but uncertainty grows as time increases. So that means if I rebalance portfolio frequently, I may have some alpha generated from machine learning model, but I may have a high transaction cost. If I rebalance my portfolio less frequently, I may have a less transaction cost, but my alpha may diminish. So I need to make a trade-off between rebalancing frequency and the transaction cost, which is determined by the turnover rate. So we're gonna discuss that issues in the next few slides. Finally, because we use prediction interval to roll out any outliers, so what is the proper coverage ratio for that interval? Should be 90%, 80%, 50%. So we can also discuss that issue. So in the next few slides, I'll be a little bit technical. So if you want to have a nap, please do so. I'm going to wake you up in a few minutes when I show results. So when I conduct data analysis, there are few aspects I'd like to consider. One is if there is a homoscedasticity. In another word, if my volatility kind of is clustered. The other one is I'm also interested in the distribution of my in the tail information. Let's say if there's a fat tail in the return distribution. Also, I'd like to know if I would like to check the relationship between the input and target. Most of the time, it's linear, but sometimes it's highly nonlinear. Think about this case. Suppose we know that temperature is a big driver for electricity consumption. So when temperature is high or low, the electricity consumption is high. When temperature is medium, so the electricity consumption is low. So this is nonlinear U-shape. Definitely, traditional linear model cannot capture it. Also, most of the time when we run linear regression model, the factors or the inputs could be very highly correlated. or we say there is a multi-collinearity within the data. Definitely we should consider. But through using machine learning model, this may not be a critical issue. The last one is stationerity. So for some, if you run time series regression, stationarity really matters. But if you run machine learning model, most of the time it's not a critical point. So let's look at the data. Here in the upper left, we have the time series of the 11 assets. So if we calculate the real return, we can see that return is pretty crazy in the crisis, and it comes down after that. So if we if we look at the distribution, probably there's a fat tail. Now let's look at the rolling volatility, 30-day rolling volatility. We see the volatility is clustered in the crisis, and then there's another one in 2014, 16, and recently. So definitely, to capture that, traditionally we can use Karch-11 or stochastic volatility model to model this feature. Let's look at the VAR as well. So you see VAR is very high in the crisis, and then it's off, and then it's on again. So there are different regimes. Definitely, there is some information, I think, embedded within the time series, and it's not easy to formalize these features within the model. So now also let's look at the performance of the individual asset. So here I just use Quantopium library to calculate these ratios. So quickly. Now if we look at the individual one, right? So if we think if we can expand the portfolio return with Taylor expansion, the first moment is the mean, second moment is the volatility, third moment is the skewness, and fourth moment is the kurtosis. So by using just the first moment and second moment volatility, we can easily calculate these ratios, so everybody knows it. But I'm also interested in the third moment and fourth moment. So just recall, if you have a normal distribution, if it's even balanced, so the skewness is 0. But if you look at the individual asset, it's either left skewed or right skewed. It's either heavily right skewed or left skewed. If you look at the fourth moment, kurtosis, for normal distribution, it's usually 3. But if you look at the number here, we have 10 for IVV, we have, I think it's around 90 for LQD. For next slice, we have 40 for EMB, so it's much, much higher than 3. This indicates that there is some rich information in the tail. And the traditional linear regression model, if we assume market cannot be predicted, this means we assume market follow random walk, so we can have different assumption for the shock. Normally we assume it's normal distribution or Brownian motion. We can, if there's a fat tail, we can assume it follows T distribution or Cauchy, but it's hard to. But when the tail is really complicated, it's hard to find a proper distribution to model the shock. I'm also interested in the relationship between the input and target. So here, if we just run the time series regression, so X, I have the prediction, Y, this is my residual. So if you see the pattern, because this is a linear regression model, so if you see the pattern, there are some nonlinear patterns within the data. However, if you use, let's say, a machine learning model, you see there's some noise, but the pattern is condensed. So this means that there are some nonlinear patterns which linear model cannot capture, but machine learning nonlinear method can capture some. This is another way to check to check if there's a nonlinearity. If there is, then we use linear regression model. Otherwise, we use nonlinear method. By the way, AR autoregressive model is a special case of recurrent neural network. So now the question is, does stationarity matter? Yes, it matters because if not stationary, now your time series will be explosive, so you cannot have a closed form solution. But however, if you look at the GRU or LSTM, they have a decaying function embedded in the gate function, activation function. So that means we impose a decaying function in the gate function so that we can stationarize data in GRU or LSTM. So that means for LSTM GRU, non-stationarity may not be an issue. Now, let's also look at the correlations among different assets. You can see that in this plot, the stock ETFs are highly correlated. And then, so another way is, so this is cross-asset correlation. If you look at the single time series, it's also autocorrelated. So if we feed these multivariate time series into time series regression model, most of the time beta would be singular. Another way to look at the correlation is look at the VIF. For example, in this example, let's say 1.7. What does it mean? It means that the variance of the particular coefficient is 70 bigger than what you would expect if there's no multicollinearity. So this is a little bit high, but this is much higher. So a thumb of rule, if VIF is greater than 5, then definitely you should drop that factor. Now let's look at the stationarity. So there are two ways to check. One is through KS test, the other is ADF test. So here, the idea is I randomly split my time series into two groups, and then I calculate the PDF, histogram, and then I calculate the CDF. I compare the distance of the two CDFs. If they are quite different, and then it means it's not time invariant. Otherwise, its time is stationary. I can also check the stationarity through the ADF test. So here you can see the ADF test shows that this time series of the return is stationary. However, the KS test says it's not. There's a conflict between the two tests. This means there are some features that one test may not discover, and maybe machine learning model can capture. All right, so I have some results to show. Next slide. So now, so we know that there are some hidden information that traditional linear regression model may not capture, and I believe machine learning model can capture some of the hidden information. So for individual asset, I just run these 10 popular machine learning models for individual assets. I just want to say, hey, which one is better? So here I have Lasso, I have ElasticNet, I have KNN, CARD, SVR. I have AdaBoost, XGB, and GBM. These three are boosting method. I have random forest, that's bagging method. ET is a tree method. So if you look at the box plots of the residuals, you can see most of the models deliver very similar results, except the card method. So for simplicity, in this test, I just choose XJB because according to the feedback that in Kaggle competition, XJB beats the other forecaster. So I just use XJB. I also to find the best parameters, I use grid search to find the best parameters for XJB. Now we have the candidate model. We use it to perform the forecasting. So here is the idea. At time t, we train a model with data. We do the prediction at t+1. And when the new data is available at t+1, I retrain the model and do the prediction again for t+2. I repeat this process again and again and again. To quantify the forecasting accuracy, I can also construct a prediction interval. This is an empirical way to do it. The idea is here. So consider IVV series, for example. At time t, I have 100 data points of the residuals, right? So for nominal coverage rate, let's say 0.1, means I want to construct 90% of the confidence interval. So I have 100 points. That is my residual. I pick the 5th point and 95th point, right? I take out these 2 points. I add them to my prediction. That's my prediction interval. But sometimes the prediction may not be, I'm not confident if the prediction is far away from the actual at t-1. So here I add another rule. If my actual data t-1 is greater than my predicted upper bound, I replace my prediction at time t with the upper bound. If my actual data at t-1 is less than my lower bound, predicted lower bound, I replace my prediction with a lower bound. Otherwise, I use my prediction. In another word, I use prediction interval to rule out any outliers. Now let's look at the. So now we're gonna see some results from different portfolios. So here's the experiment setup. Here we have 11 years data from 2008 January all the way to this month. For training, we have 5 years data. We have 5 years data for training, 3 years data for validation, and 2 years data for testing. For all the portfolios we construct, it's long only. We don't short. Also, remember we have 11 assets. So here, I just say, what about if I just buy and hold? I can also have an equal allocation, buy and hold. I can also have a portfolio, equal allocation, buy and hold. So now these would be the benchmark I'm gonna compare. I also have another few construct portfolio. One is dynamic equal allocation. The other two, so I have maximum Sharpe ratio, I have minimum variance. I can either fit the return with historical mean, or I can either fit, I can use predicted return. I can feed it to the optimizer. So I have another five portfolios. So here, I'm trying to say, hey, if I rebalance, what about, so I want to see what is the difference if I rebalance portfolio daily versus weekly or monthly? So we can see that if we rebalance portfolio daily, all the alpha are eaten by the transaction cost. So we have negative returns. If we rebalance portfolio monthly, now we have some positive return, and Sharpe ratio is around 1.5. Here, the transaction cost, I assume, is just 10 basis points. I also, so remember the transaction cost is determined by, the aggregate transaction cost will be determined by turnover rate. So I have another constraint for turnover rate. Let's say, well, by the way, turnover rate is a measure the distance between the optimal allocation and the existing allocation. So if I relax the constraint for turnover rate from 40%, this is one way, to 50%, 60%, if we relax a bit, we can see from Sharpe ratio, the performance is improved a bit. That's potential reason, the best results I got is just I don't have a constraint for turnover. It's the best. I think the reason may be because I have a very low transaction cost. If I increase transaction cost from 10 to 20 or 50, results would be very different. Last test, I'm also very interested in the, so here, let's look at the box plots for individual returns. We can see that so if you look at the box plots, the return is kind of evenly distributed. There are not much tails in the distribution. So for nominal rate, let's say 0.1, we can construct 90% prediction interval, and the corresponding Sharpe ratio is 1.5. If we further decrease the prediction interval, the coverage ratio, the performance actually decreases. So the last one, no prediction interval, this means that I just use the prediction. I don't use prediction interval to rule out any outliers. You can see it's not bad, but definitely with the help of prediction interval, we can rule out some outliers. So performance is much improved with the help of prediction interval. I'm almost done. So here, this is a performance from this is a performance of the right one is a cumulative return from the suggested portfolio. This is minimum variance portfolio. So I rebalance monthly. I have 90% prediction interval. So here you can see, even there is a shock late last year, this portfolio is not much impacted. We also fit the P&L to the factor model, 3 factor and 5 factors. The alpha is around 0.9, and we have low beta here. The R square is around 0.2. All right, so let's sum up. So in comparison to the traditional linear regression model, I think machine learning model is able to capture the nonlinearity between the input and target. Moreover, nonlinear method can capture the complicated features among the multi-dimensional, multivariate data. With the help of prediction interval, we can rule out any outliers in the prediction so that we can have a better performance. The last one, there needs a trade-off between the rebalancing frequency and turnover rate. If the portfolio is rebalanced frequently, meaning we look into a short-term horizon every time, the aggregated transaction cost due to high turnover rate may eat all the alpha, may eat the short-term alpha. However, if the portfolio is rebalanced less frequently, meaning we only look into a long-term horizon every time, the alpha generated from ML may diminish due to the uncertainties in the future. So with that, thank you. Any questions, comments? Please.
So just to understand, the features you use are data in the past, right?
Yes.
Okay, so you just basically fit it a
Time
time
series of
series, just the time series,
prices.
or every single security,
What's that?
every single name, every single security over
Yeah.
there.
Yeah.
Okay.
Yeah. Definitely. You can use factor models. You can feed some other signals, but this is a simple toy portfolio. Yeah. Just want to demonstrate that there is a benefit using machine learning model for prediction. Thank you.
All right, we have time for one more question.
I saw you tune the hyperparameter, the estimator number. Do you do other hyperparameter tuning during your training session?
For machine learning models. So I just use so here I use libraries from Python, multiple libraries. Most of the time I just use default parameters. And then once I choose SGB, I use grid search to find the best parameters. So I use tenfold cross validation. No, I just did one.
All right, thank
Thank
you
you.
so much. Let's give him a round of applause.